Okay, so hi everybody, welcome back. Today we're going to be starting a new chapter. This is chapter 36 of the textbook, and this will be the last chapter that we cover in this class. Now, this is also one of my favorite chapters to teach because the theory of relativity is absolutely mind-blowing. There's a ton of really counterintuitive stuff that we're going to learn about here. And as we learn the theory of relativity, we're going to find that a lot of our intuitions, a lot of things we commonly accept about the way space and time work is actually wrong. And as we learn the theory of relativity, we're going to get a much deeper understanding of the nature of space and time. But in doing so, again, we're going to have to challenge a lot of the assumptions and intuitions that we have. So because the theory of relativity is so counterintuitive, I do want to give you a little bit of a history behind it. How did it come to be that we went from Newton's laws, Newtonian mechanics, to our modern day understanding of relativity? That deserves an explanation because, of course, a lot of the things that relativity is saying are so counterintuitive. So let's get into this. I'm going to start off with a question for you guys to think about. This is sort of just to test your intuition, okay? So Alice and Bob are on a moving walkway, which has a constant speed of 1 meter per second. So this is the type of thing you might see at an airport to help you get to your gate faster. The walkway itself here is moving at 1 meter per second. So we have Claire standing on the ground next to the walkway. So she's standing still with respect to the ground. Alice is on the walkway, as we see here, and she is standing still. So she's at rest relative to the walkway. And she observes Bob walking ahead of her with a constant speed of 1 meter per second. Okay, so Alice would say that Bob is moving ahead of her at 1 meter per second. But what would Claire say that Bob's speed is? Okay, what would the speed of this guy be from the perspective of Claire? So try to just do this intuitively. Don't even write anything down. Just intuitively, what is the answer? Pause the video, think about it for a second, and then come back to it. Okay, so we know intuitively that we just need to add the two speeds together. We take 1 meter per second for the speed of the walkway relative to Claire, and then we add to that 1 meter per second for the speed of Bob relative to the walkway. And then we just take 1 plus 1, which is 2 meters per second. So the intuition we have is just to add those two speeds together. And this is the right answer. 2 meters per second is the correct answer here. But it turns out simply adding the speeds together, as we just did here, doesn't always work. That can start to break down in certain situations, and we'll, of course, get to that later. So what we used in that example problem that we just did, something called Galilean Relativity. This is something that was worked out in the early 1600s by the Italian physicist Galileo. And the idea here is that motion is relative. It's not absolute. If we want to measure any sort of feature of an object's motion, like velocity, we want to measure its acceleration or anything else, we first need to define our frame of reference. Okay? Without a frame of reference, it's meaningless to talk about an object's velocity or acceleration or anything else. So a frame of reference is just a coordinate system. It's just a set of coordinates that we use in order to analyze an object's motion. And typically, we fix that coordinate system to an object or an observer. And as an example, let's say I'm driving and my speedometer on my car reads 45 miles per hour. What that actually means, of course, is I'm moving at 45 miles per hour relative to the ground, but relative to my car, I'm not moving at all. I'm stationary with respect to my car. So the idea here is the description of my motion, okay, if you wanted to say what my speed is, for example, you'd have to first tell me what frame of reference you're measuring it in. In the frame of reference that's fixed to my car, my speed is 0. In a frame of reference fixed to the ground, my speed is 45 miles per hour. Neither of those two statements is the correct one. They're both correct, right? Which is to say that my motion is relative. It's not some sort of absolute statement you can make. You can never say, I'm absolutely at rest. Well, in one frame of reference, you might be at rest. In another one, you won't be. That is the idea behind this statement that your motion is relative and it's not an absolute thing. Okay, so the next thing we have here is what's called the Galilean transformation. Okay, this is an equation that allows you to switch between two frames of reference that are moving at a constant velocity relative to one another. Now, in this equation, we are simply adding two velocity vectors over here and then getting out a third velocity vector over here. But we have to be really careful with the notation. So each velocity in this equation has two subscripts, okay? This is how you interpret the subscripts, okay? The first one is what's moving, okay? The second one is which frame of reference we're measuring that motion with respect to. So for example, let's take a look at the very first term in our equation. This says VOA. That means the velocity of some object with respect to frame of reference A, okay? That's equal to the velocity of that same object with respect to frame of reference B, that's how you interpret VOB here, plus the velocity of frame of reference B with respect to frame of reference A. That's how you interpret this equation. And you know you set it up right when we have a subscript on the left side that matches the subscript on the left side over here on the other side of the equation, a subscript on the right side which matches the subscript on the right side over here, and then the inner subscripts, B in this case, don't actually appear on this side of the equation. Okay, so that's just how you set it up visually, but this is what it means, okay? We're going from the velocity of an object in one frame of reference to the velocity of an object in another frame of reference. That's what this allows you to do. So let's apply that equation to the problem that we just did. So for that example, this is the notation. A is going to represent Alice's frame of reference. So imagine this is a coordinate system that is following Alice around. It's fixed to Alice. And then we have B, which stands in for Bob. That will be the object in question that we want to know the velocity of. And then C will be Claire's frame of reference. Again, just imagine that's a set of coordinates that is just attached to Claire. So in Galilean relativity, we know that we can simply add the velocities. So if I want to know VBC, that would be the velocity of Bob as seen by Claire. That would be VBA, the velocity of Bob as seen by Alice, plus VAC, the velocity of Alice as seen by Claire. And again, we know we set the equation up right because we have B as our subscript on the left side over here on this side of the equation. That matches with the other side of the equation. It's on the left side here. C is on the right side. And then the inner subscripts A just don't appear on this side of the equation at all. So we know we've set it up properly. Okay, but when it comes down to plugging in the numbers, this is really simple because we have 1 meter per second times I hat, so just in the x direction for VBA. Bob is moving at 1 meter per second in the x direction relative to Alice. And then we're adding that to 1 meter per second I hat for VAC because, of course, Alice is moving forward at 1 meter per second in the x direction relative to Claire. So that's how we knew intuitively to add those two together to get 2 meters per second in the x direction. That's what Claire would see as Bob's velocity. Okay, now an unstated assumption of Galilean relativity, that is an assumption that you have to make in order to derive this equation here, is that time is absolute. So even though we may disagree about speeds, if you're in one frame of reference, you may measure a different speed as someone in a different frame of reference. For example, Alice and Claire have two different speeds they measure for Bob. That's all fine. But we will agree on the amount of time that has passed between two events. That's the assumption in Galilean relativity, is that time is absolute. We're all going to agree on the amount of time that's passed. So it turns out that's wrong, okay? And as we start to understand Einstein's theory of relativity, we're going to see how the idea that time is absolute is incorrect. But we'll work our way towards that. So let's just do one more Galilean relativity problem before we move on. We have a river that flows from west to east at a speed of 1 meter per second. That's relative to the shore. That's how fast the river is flowing. You can row your boat at a speed of 1 meter per second. That's measured relative to the water. Now, if you're starting out at the south shore over here, and you point your boat straight north and start rowing at full speed, what is your velocity with respect to the shore going to be? Okay, so in other words, if I'm standing here on the shore, how fast and in what direction am I going to see your boat moving? So we'll define our coordinates in this way. We're going to have east be the positive x direction and north be the positive y direction. Again, which one of these velocities here describes my boat moving relative to the shore? So pause the video, try to work it out, and then we'll go through it together. Okay, so we'll start with the notation. So G is going to represent a frame of reference that's fixed to the ground. R is going to represent a frame of reference that's moving with the river. So for example, if you were just on a raft floating down the river and not moving with respect to the water, that would be frame of reference R. Now B represents the boat. That's the object that we want to know the motion of. So the Galilean transformation tells us that VBG, that's the velocity of the boat relative to the ground, that's what we want to know, is equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. Again, that's just how we set the equation up. But we know each one of the velocities that goes into this. We know that VBR, the velocity of the boat relative to the river, is 1 meter per second. That's how fast you can row your boat relative to the river. And you're pointing your boat straight north, so J hat is straight north or the y direction. But the river is moving in the positive x direction relative to the ground. So VRG is 1 meter per second, I hat. Okay, so this would be the answer. 1 meter per second I hat plus 1 meter per second J hat, meaning if we show this vector as an arrow on our diagram, it looks like this. So just as much of an x component as there is a y component. That means the boat appears to be heading northeast. Okay, relative to the shore, relative to the ground. Let's say relative to an observer on the ground. Okay, that's how you do this one. Okay, so let's jump ahead in our history to the late 1600s, which is around the time when Isaac Newton was coming up with his 3 laws of motion. So we want to understand how Isaac Newton thought about relativity. How did Isaac Newton think about how motion can appear different depending on your frame of reference? So let's go to Newton's first law as our starting point. Newton's first law says that an object moves at constant velocity unless acted upon by an unbalanced force. In other words, if the net force acting on an object is 0, then it's not going to accelerate, it's going to move at constant velocity. That's the idea. So let's take a look at an example. Here we have a truck that is carrying an unsecured box. So the box is not tied down. There's no friction between the box and the bed of the truck. And also the back of the truck is open, so the box is free to slide out. So this truck is going to start off at rest, but then accelerate forward, okay? So we want to understand what this motion of the box looks like from two different perspectives. So first, we'll take the perspective of this guy who's just standing on the ground. So the frame of reference is right here. It's an XY coordinate system attached to this person. We're also going to think about the perspective of someone who's riding in the truck. So the frame of reference here would be X prime, Y prime. These are coordinates that are moving along with the truck. Okay, so let's take a look at an animation. This is what the person standing on the ground will see. The truck accelerates forward, and then the box doesn't move at all in the X direction, but as soon as the truck has moved away, it falls straight down in the Y direction. So that's what we see. So what happened is there was no force on the box in the X direction. There was no friction or any other type of force acting on this box in that direction. And therefore, since we had zero net force in the X direction, we had zero acceleration in the X direction. And that's exactly what we saw. The box simply didn't move in the X direction. That's exactly in accordance with Newton's first law. So now let's take a different perspective. Let's try to see what things look like from this frame of reference that's moving with the truck. So here's an animation that shows us what things look like when we're moving with the truck. And of course, what we see is the truck doesn't appear to be moving. It's at rest with respect to these coordinates. But the box and the person, for that matter, accelerated backwards in the negative X direction, okay? And there's actually a problem with that because from the truck's frame of reference, the box did accelerate. It accelerated in the negative X direction, even though, as we said before, there's no force acting on it in that direction. There's nothing pushing it out the back in the negative X direction. So this seems to contradict Newton's first law because we have zero net force acting on the box, yet it is accelerating in the negative X direction. That seems to contradict Newton's first law. And so the way that we resolve this contradiction is to bring in the idea of an inertial reference frame. This is a really important idea. So an inertial reference frame is a coordinate system that is not accelerating. If you have a set of coordinates that's not accelerating, that's an inertial reference frame. In other words, the coordinates can move at constant velocity, but they can't be accelerating. So the problem with the previous example is that the truck's coordinate system was accelerating, okay? It was accelerating along with the truck. And that would be a non-inertial reference frame because, again, the coordinates are accelerating. Now, Newton's laws are only valid if we're using an inertial reference frame, not accelerating, to measure the motion. And so, as an example, let's take Newton's second law. In any inertial reference frame, Newton's second law takes on the familiar form that we've seen a million times before. The net force acting on an object is equal to its mass times its acceleration. It turns out if we use a non-inertial reference frame, in other words, if we want to use a set of coordinates that is accelerating, then this equation has to be modified. It's not simply F equals ma anymore. On the left side, we still have the net force, and then we have mass times acceleration, which is the second derivative of position. That's what's shown over here. But you also have these extra terms in the equation, which are called fictitious forces. We're not really going to concern ourselves with what these extra terms mean. The point I'm trying to make here is that one of our laws of physics, Newton's second law, looks different in inertial reference frames compared to non-inertial reference frames. Okay, it looks much simpler in inertial frames. In a non-inertial reference frame, it's more complicated. There's extra terms in it. So to give you a sense of how physics works a little bit differently in a non-inertial reference frame compared to an inertial reference frame, which is what we typically use, I'm going to show you a video. And this video comes from MIT, so credit where credit is due. I left the link down here. This is where I found this video, and you can click that link and see it again on your own time. But let's watch it here, and I'm going to point out some things in the video that I want you to take note of. So we have two experimenters on a platform which can rotate. And what they're going to do is play a game of catch. They're just going to throw this ball back and forth while they're sitting on the platform. And right now it's not very interesting because the platform isn't rotating. But now the platform is rotating, and you can see they're having a hard time actually throwing the ball to where they want it to go. So we can see why this is happening. Let's first take the perspective of someone who's just standing on the ground, not rotating with the platform. This camera is not rotating with the platform, and we can see from a bird's eye view what the motion of the ball looks like. There's actually nothing unexpected about the motion of the ball. It moves in the same trajectory we'd expect it to. It's just that the person is rotating out from underneath it. But if we take the perspective of the rotating platform, which is a non-inertial reference frame, things look different now. The ball appears to curve. It appears to curve horizontally. You can see it in slow motion, even though we know there's no force pushing it that way. Okay? Again, this is just another effect of being in a non-inertial reference frame. We're going to see objects accelerate with no apparent force causing it to do that. Again, the ball accelerates and curves off to the left. There's no force pushing it that way, but since we're in a non-inertial reference frame, that's the way the ball moves. And of course, that's why they're having a hard time playing catch, because they're not anticipating the ball curving away from the path they're trying to throw it in. And this effect is called the Coriolis effect, by the way. You may have heard of this. It's part of the reason we get large-scale weather patterns like hurricanes and cyclones. But what it causes to happen here in this case is the ball to curve away from the expected path. So of course, with a little bit of practice, they can get used to the Coriolis effect and throw the ball in the right path. But again, this is just one of the many effects of being in a non-inertial reference frame. The laws of physics look different. They take on a different form in a non-inertial reference frame, and that has very apparent consequences. So that takes us to the relativity principle. The idea here is that Newton's laws will take on their simplest form in an inertial frame of reference. I showed you one example already. It's F equals ma in inertial reference frames. The equation is more complicated with more terms in it when we're using a non-inertial reference frame. So in this sense, inertial reference frames are special, or they're preferred compared to non-inertial reference frames because, again, the laws of physics take on a simpler, more compact form in inertial reference frames. It's also true that Newton's laws have the exact same form in every inertial reference frame. So if we take a look at two non-inertial reference frames, the equation for Newton's second law may take on slightly different forms. They may be slightly different sets of terms that we have to account for depending on how the frame is accelerating. But if we're in an inertial frame that's not accelerating, it's just F equals ma every single time. Newton's laws have the exact same form in every single inertial reference frame. So that's to say that there is no special inertial reference frame. Any set of coordinates that's moving at constant velocity works just as well as any other. According to Newton's laws, we don't prefer any one inertial reference frame over another because the form of the equations looks exactly the same in every single inertial reference frame. So that's really the essence of what we call the relativity principle. The idea is that the laws of physics take on the exact same form in any inertial frame. That's the relativity principle. So now let's take a look at Maxwell's equations. I alluded to these earlier. If you've taken Physics 46, you'll have some idea of what these equations are all about. If you haven't seen these before, again, don't worry. I'm just going to run through them real quick, and we'll see how they relate to the relativity principle. So Maxwell's equations describe how electric charges and electric currents, that is just moving charge, can create electric and magnetic fields. Okay, so if you have some electric charge or if you have some electric current, you can then calculate how that creates an electric field, which is given by E, and a magnetic field, which is given by B. So these are the four equations that Maxwell came up with. There are a few constants in the equations. We have this thing called mu naught, which appears here, and we have this thing called epsilon naught, which appears here and here. So if we take those equations and we say that we're in a region of perfectly empty space, so there are no electric charges, that means we set this term rho equal to 0 here, and there are no electric currents, which means we set this term J equal to 0 here, we can get these equations to reduce to the following. We have the second derivative of E, that's the electric field with respect to time, equals 1 over mu naught times epsilon naught, times the second derivative of E with respect to x. And then we also have the second derivative of B with respect to time equals 1 over mu naught times epsilon naught, times the second derivative of B with respect to x squared. Okay, so in perfectly empty space, this is what we can get Maxwell's equations to sort of boil down to. Of course, that takes some work, and I'm not going to show that, but we can go from here to here in the case where we have perfectly empty space. Okay, you should recognize the form of those equations. Okay, each one of these is a wave equation. It describes a wave of oscillating electric and magnetic fields. And the speed of the wave is present in the wave equation. This is actually the speed squared right here, this constant out in front of the second derivative with respect to x. So the speed of the wave we're talking about is the square root of that. So let's call that speed c. That would be the square root of 1 divided by epsilon naught times mu naught. And if we plug those values in, you can actually try this out. Here's what you'll get. 3 times 10 to the 8 meters per second. So it was known during Maxwell's time that the speed of light was equal to 3 times 10 to the 8 meters per second. And it's no coincidence that when we calculate the speed of this wave of oscillating electric and magnetic fields, that it's exactly equal to the speed of light. So according to Maxwell, this is how we should think about a light wave. We have an oscillating electric field, in this case oscillating in the y direction. We have an oscillating magnetic field, in this case in the z direction. And then the wave itself moves perpendicular to both of those directions, so this wave is moving in the positive x direction. Now, if we think back to every other type of wave that we've seen before, a wave needs a medium in order to propagate. If we have a wave on a string, you obviously need that physical medium of the string in order for the wave to move. In the case of sound, you need the air for sound to move through. You need some sort of material for the wave to actually propagate. So it was natural to think that light is the same sort of thing, where a light wave needs a medium, it needs something that it moves through. So physicists needed to explain how light can travel through what appears to be perfectly empty space. So let's take the example of sunlight. Light that's emitted by the sun has to travel through about 93 million miles of almost perfectly empty space before it reaches the Earth. So a wave needs a medium. How is it that light is traveling through empty space where there appears to be no medium? Well, by the mid-1800s, the solution that most physicists agreed upon was that actually what appears to be empty space is actually filled with a substance. Okay? There's something out there called the ether, which fills all of space, and that's the medium that light moves through. We just haven't detected the ether yet. We don't know it's there, but they figured it has to be there just to explain how light moves from the sun to the earth, as an example. But the idea of the ether poses a challenge to the relativity principle. So let's say the ether is real. There actually is this substance that fills all of space called the ether. If that were true, then that would be a special inertial reference frame. What I mean by that is Maxwell's equations would take on their simplest form in a reference frame that is not moving relative to the ether. But they would take on a different form in a reference frame that is moving relative to the ether, even at a constant velocity. So again, that would seem to violate the relativity principle because all inertial reference frames should be on equal footing. There shouldn't be a special one that is different from the others, okay? So just keep that in the back of your mind while we do this next example problem. So we have Alice riding on a train, which is moving at half of the speed of light. So the velocity of Alice relative to the ground, of course, is 0.5 c. Now, Bob is standing on the train tracks directly in front of the oncoming train. Alice shines a light at Bob to warn him to get out of the way. The question for us is, how fast does Bob see that beam of light approaching him? Is it going to be 1.5 times c? Is it just going to be 1 c? Or is it going to be 0.5 times c? So pause the video, think about this for a minute, and then see if you can get an answer. So let's try applying the Galilean transformation to this problem, where we're going to use the notation L for the light beam, A for Alice's frame of reference, and then B for Bob's frame of reference. Okay, so Alice's frame of reference is just a coordinate system that's moving along with Alice like this. Let's have the positive x direction be going to the left because that's the way everything is moving here. And then Bob has his own frame of reference, a set of coordinates that is fixed to him, and that's what we call B. Again, positive x direction, let's just have that going to the left in this case. So according to the Galilean transformation, VLB, that would be the velocity of the light beam relative to Bob, should equal VLA, velocity of the light beam relative to Alice, plus the velocity of Alice relative to Bob. So we simply add the velocities together, and then we get the velocity of the light beam relative to Bob. So VLA, that's, well, c. So Alice sees that light beam moving at the speed of light c in the positive x direction, so there's an I hat. And then Bob sees Alice coming at him, also in the positive x direction at 0.5 c. So there's an I hat next to that. So if we add those together, we'd get 1.5 times c times I hat. And then we'd conclude that the answer is 1.5 times c. But that's actually completely wrong. It does not work that way. Okay? The speed of light, as it turns out, does not change. It doesn't matter what frame of reference you're observing it in. It doesn't matter how fast the source of the light is moving towards you or away from you. You still see it moving at the exact same speed c. Okay, that's the claim I'm making here. And in order for that to be true, the Galilean transformation, this breaks down at some level. It breaks down when things are moving close to the speed of light. So it's perfectly fine to use this if we're talking about rowing your boat across a river or a moving walkway in an airport where things are moving really slow compared to the speed of light. But my claim is when things move close to light speed, this equation just doesn't even work anymore, and it's going to give you the wrong answers. And a really counterintuitive result is that the speed of light is the speed of light, and it can't change even if you change your frame of reference, okay? And so that takes us to the Michelson-Morley experiment, which was carried out in 1887 for the first time. And it's one of the most famous experiments in all of the history of physics. So here's the basic rundown of this experiment. An interferometer, this is the device shown here, was designed to detect the motion of the Earth through the ether. The idea is, if the ether is really there, if there really is this substance filling all of space, we should be able to detect how Earth is moving through the ether. Earth is, of course, orbiting the sun and rotating on its axis, so it's moving through this substance in different ways. We should be able to detect that specifically by measuring variations in the speed of light. So here's how the device works. We have a light source, which emits a beam of light going this way to the right at first. Then it encounters a beam splitter. So it's exactly what it sounds like. The beam splitter splits the beam in half so that half the beam goes this way along this arm, which is oriented north. And then another part of the beam goes straight through, and it goes along this arm, which is oriented east. Now here's the thing. The one that's oriented north is perpendicular to the direction of Earth's rotation, but the one that's oriented east like this is actually parallel to the direction of Earth's rotation. And so what everybody expected to see was a different speed of light for the beam that's traveling along this arm in the direction of Earth's rotation compared to this one, which is, again, perpendicular to Earth's rotation. And the way we can determine whether that's happening is to notice what happens after the beam travels all the way down each arm. So at the end of each of the arms of the interferometer, we have a mirror. So now the beam gets sent back towards the beam splitter. So the beam traveling back to the left this way, some of it is going to hit the beam splitter and now be directed down this way, straight down. And same thing goes for this beam that's traveling along this arm. It goes up, hits the mirror, comes back down, and then some of it goes through the beam splitter and then travels straight down this way. So the two outgoing beams are over here, and they go into a detector. Now, if the speed of light is different for the two beams, then the two waves are going to become out of phase with one another. If the speed of light is the exact same thing for the two beams, then they will be perfectly in phase by the time they hit the detector. Okay? And let's see what actually happened in this experiment. So in the real experiment, when we send the beam of light through this device and then back into the detector, we see that the waves never go out of phase, not one bit out of phase, meaning the speed of light is the exact same thing for this beam and for this beam, because again, we can tell that they're never going out of phase. And this experiment was tried many, many times because people were super confused about this result. They wanted to really see if this was a real result. And no matter how many times people redid the experiment, no matter how they reoriented the interferometer, the speed of light never changed. And so this idea that there is an ether filling all of space that light moves through, and depending on how you're moving relative to the ether, you can see a different speed of light. That's something that almost everyone accepted at the time. That idea had to be abandoned. It was just experimentally shown that it was wrong. The speed of light doesn't change. There is no ether. So the Michelson-Morley experiment left a lot of physicists feeling very confused and not knowing how to move forward. So in 1905, Albert Einstein comes along and he really clears things up. He makes things make sense again. So again, back in 1905, when Einstein was only 26 years old, he formulated his theory of special relativity. The entire theory was worked out starting from two simple postulates. Number one, the laws of physics take on their simplest form in any inertial frame of reference. That's basically a restatement of the relativity principle that I showed you earlier. And then number two, light moves through empty space at c equals 3.00 times 10 to the 8 meters per second. And that speed is independent of the motion of the source of that light or the observer of that light. Everyone agrees that c is equal to this value. Again, all of the theory of special relativity comes from these two very simple starting points. And so I'm going to show you how we develop the theory starting from here. And it's going to take us to the famous equation E equals mc squared that you may have seen before. But what Einstein is doing here in coming up with the theory of relativity and starting from these two postulates is he's fully accepting the idea that the speed of light is an absolute quantity, okay? We're not going to disagree about the value of c. It's going to be the same for every observer. Now, in accepting that the speed of light is absolute, it led him to the idea that length and time are relative. So what we thought of as absolute quantities before, like the length of an object or how much time has passed, those are actually relative things that depend on the frame of reference you're in. So this is the starting point, and that's sort of the history behind the theory of relativity. So now let's start getting into what the theory of relativity has to say. And the first topic is something called time dilation. So I'm going to show you a famous thought experiment that Einstein came up with to try to understand how motion can affect the passage of time. So this is called the light clock. This is a hypothetical device, of course. It was never actually built by Einstein, but he just used it to sort of think through what would happen. So for the light clock, we have a light source, something that emits a beam of light, and then a mirror, which is a distance d away from that light source. So the light source sends out the beam, and then it reflects off the mirror, and then it comes back, and then it hits a detector. So the idea is we can actually measure the passage of time because we know the speed that the light beam moves with, and we also know the distance that it has to travel. So we can figure out how long it takes to get from the source back to the detector, and we can use that as a sort of clock. So as measured in the clock's frame of reference, okay, so if we're using a frame of reference where we see the clock stationary, not moving, the time it takes to go from the source off the mirror and then back to the detector, we'll call that delta t naught, is going to be given by, well, the fact that speed is distance over time can be used here. And the speed we're talking about is c, because it's a light beam. And the distance it has to travel is 2 times capital D. And then the time it takes is delta t naught, as we just said. So therefore, we can rearrange this to say that delta t naught is 2d divided by c, okay? That's the time it takes in the clock's frame of reference, again, for the beam to go from the source, off the mirror, and then back into the detector, okay? But now let's take a look at things from a different frame of reference. Let's suppose this light clock is actually in a spaceship that's moving to the right at speed v relative to a person standing on Earth. Okay, so this entire light clock device is going to be moving to the right at speed v, and we want to take the perspective of this person standing still on Earth. So this is what the situation would look like in that frame of reference. Light gets emitted, bounces off the mirror, back into the detector, but the whole time the entire clock is moving to the right. Let's see it one more time. Okay, so that's what happens. And so the path that the light beam took is actually a little bit different in this frame of reference. It moves diagonally up and to the right like this, hits the mirror, and then back down diagonally down and to the right like this to get back to the detector. This is the path the light beam takes in this frame of reference. And so let's label a couple different distances on this diagram. We have d, which is the vertical distance you see here. And that's, of course, the same as before, the distance between the source and the detector down here and the mirror up here. But we also have a horizontal distance L, which is half of the total distance that the light clock travels to get from the initial position here to the final position here. Okay? So notice something about the total distance that the light has to travel. In the person's frame of reference, we see this pulse of light travel a greater distance than before, a greater distance than if we were in the clock's frame. Now remember, the speed of light is a constant. The observed speed of light can't change depending on our frame of reference. So whether we're in the person's frame down here or in the frame of the clock, we're going to see the same exact speed of light. But again, the distance just increased. So if the distance increases, but the speed stays the same, that means the time also has to increase. In other words, the observed time between the emission of that pulse of light and the detection of the pulse of light, let's call that delta t, is greater in this frame of reference compared to the clock's frame of reference. So in other words, the two frames of reference are not going to agree on the amount of time that passed. So now let's do a little bit of a derivation. We know that speed is equal to distance divided by time, which means distance is equal to speed times time. So we're going to apply that to this situation where we have a light pulse traveling as observed in the person's frame of reference. So first of all, what is the total distance that the light pulse has to travel? Well, the one-way distance to get from the source to the mirror is this hypotenuse of a right triangle. And we have to double that to get the total distance. So we have 2 times this hypotenuse, which is equal to the square root of d squared plus L squared. That's just the Pythagorean theorem. Again, we have to double that to get the total round trip distance. Now, how fast is this light beam going? Well, it's c, the speed of light. And then how long did it take? We're calling that delta t. Okay? So next, let's think about the distance L that we see on the diagram here. L is half of the distance that the ship moves as we go from this initial position to this final position here. So using the same idea that distance is equal to speed times time, we'll have L is equal to 1/2 of the total distance the ship travels from here to here. So we have 1/2 of the speed of the ship. Now that's V, okay, not C, that's the speed of the ship, not the speed of light, times delta t, that's L. Okay, so we'll plug that in. We have the square root of d squared plus 1/2 times V times delta t squared, equaling c times delta t. And if we square both sides, here's what we'll get. So the 2 becomes a 4 when we square it, and the square root here goes away. And then expanding out what's in the square root, we have d squared plus 1/4 times v squared plus delta t squared, all in parentheses. And then we have on this side c squared plus delta t squared. So what we can do is we can distribute the 4 into the parentheses, and we'll have 4 times d squared. But then the 4 will cancel with this 1/4 factor over here. And so we'll just have v squared times delta t squared. So we'll take that term and subtract it, so we move it over here to the right side of the equation. So what we have is 4d squared is equal to c squared delta t squared minus v squared delta t squared. Okay, so we'll do a little bit of factoring out common terms. So we have 4d squared over here. I can pull out a factor of c squared from this term, and I can also pull out a factor of delta t squared, which will leave us in parentheses with this, 1 minus v squared over c squared. okay? That's a way of factoring the right-hand side of the equation out. So to rearrange that and solve for delta t, the first thing I'd want to do is divide this whole thing out, and then I'll want to take the square root. So on top, I'll have 4d squared divided by c squared, but if I take the square root of that, I'll get 2d divided by c on top. Then on the bottom, I'll have this thing in parentheses, but after I take the square root, I'll have the square root of 1 minus v squared divided by c squared, okay? The last thing to notice is that what we see on top here, 2d divided by c, that's delta t naught. That's the amount of time that passes in the clock's frame of reference, okay? So what we just derived is delta t, the amount of time that passes in the person's frame of reference, is equal to delta t naught, the amount of time that passes in the clock's frame of reference, divided by 1 minus v squared over c squared. That's the relationship between the two times. This is how we can see that the amount of time that passes is not the same in these two different frames of reference. So what we've just derived is an equation that describes time dilation. This is the idea that different observers will not necessarily agree on the amount of time that passes between two events. So if we take the example of the light clock that we just looked at, the two events would be 1, the light pulse gets emitted, and then 2, the light pulse gets detected. Those would be the two different events. And then delta t would be the time that passes between the two events. We see that we get a different delta t depending on which frame of reference we're observing this in. So in our equation, delta t naught is what we call the proper time. This is the time that elapses between the two events as measured in a frame where the two events occur in the same location. So in the frame of the light clock, the two events, the light pulse being emitted and the light pulse being absorbed, occur at the same location. So that would be the proper time, delta t naught, as observed in the frame of the light clock itself. Delta t is the time between the two events observed in a different frame, one that's moving at some speed v relative to that proper frame. So in our example of the light clock, delta t would be the time observed by the person standing on the ground, not moving with the light clock. So the relationship between those two delta t's is delta t equals delta t naught, that's the proper time on top, divided by the square root of 1 minus v squared over c squared. Now, this term 1 over the square root of 1 minus v squared over c squared is going to come up a lot. So we'll define that to be a constant called gamma. So again, gamma is equal to 1 over the square root of 1 minus v squared over c squared. So then delta t would just be gamma times delta t naught. So if we take a close look at the expression for gamma, this is always going to be something at least equal to 1 or greater than 1, which means delta t is always going to be bigger than delta t naught. So the proper time, delta t naught, is the shortest time interval that any observer can measure. Okay? That is to say that delta t is always greater than or equal to delta t naught. You can't get smaller than the proper time, delta t naught. So let's take a closer look now at the gamma factor. In general, gamma tells us how significant relativistic effects are. Okay, so sometimes relativistic effects are not very important and you can ignore them. Other times they're very important. And the value that gamma takes tells you which of those regimes you're in. So for example, time dilation. Delta t is equal to gamma times delta t 0. If gamma is just equal to 1, then these two times are the same, so time dilation isn't really important. If gamma is a big number, then these two times are very different, and time dilation is a very important effect. So gamma sort of sets the scale. It tells us how important relativistic effects are, And gamma appears in all sorts of equations in the theory of relativity. This is just the first one we've seen. It's going to keep popping up. So gamma is equal to 1 over the square root of 1 minus v squared over c squared. So let's take v to be equal to 0. That means you have two frames of reference and they're not moving at all with respect to one another. Well, if you do that, then you get 1 over 1, which is just 1. So the smallest value gamma can have is 1. That's when there's no movement at all, v is equal to 0. We call this non-relativistic because if gamma is equal to 1 or close to 1, then relativistic effects are really not important. On the other hand, if we take v in the limit where it approaches c, so what if we plugged in c to this equation? We would get, well, c squared over c squared here, which is 1, and then we'd have 1 minus 1, which is 0, but then we'd be dividing by 0. So in the limit where v goes to c, where you approach the speed of light, in other words, gamma approaches infinity. So when gamma gets really, really big, that's what we call hyper-relativistic, okay? When you're approaching the speed of light, relativistic effects become really important. So if we take a look at a graph of gamma versus v, we'll see that, again, when v is equal to 0, 0 speed, that means gamma is equal to 1. And then as you increase the speed, gamma does increase, but very, very slowly. So it stays very close to 1 at low speeds. But then, as the speed begins to approach the speed of light c, gamma starts to get out of control. It increases at an ever-increasing rate. And in fact, as v goes to c, this line becomes completely vertical. In other words, the gamma factor diverges as v goes to c. It goes off to infinity, okay? Now also notice that if we consider speeds that are greater than c, if we consider traveling faster than the speed of light, there actually is no value of gamma that corresponds to that, right? The graph basically diverges here. There is no greater than light speed travel that corresponds to a real value of gamma. In other words, if we plug in a value of v right here, that's greater than c, okay? Then you're going to get something greater than 1 for v squared over c squared. But then you'll be taking 1 minus something that's greater than 1, which is a negative number. And then you'll be taking the square root of that. Well, taking the square root of a negative number is what we call imaginary, all right? It's not a real number. In other words, there's no real value of gamma that corresponds to a speed greater than the speed of light. And that implies that traveling faster than light is impossible. It's mathematically impossible if you take this equation seriously. So with that said, here's a question for you guys to think about. At what speed is the gamma factor equal to 1.10? And then at what speed is the gamma factor equal to 3.00? Give your answers in meters per second. So pause the video, use this formula for the gamma factor to work this out, and then come back to it when you think you have your answers. So we'll start with the definition of gamma. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. And the first thing we'll do is square both sides of the equation. So we have gamma squared on the left. 1 squared is still 1, but then on the bottom, now we've just gotten rid of the square root. It's 1 minus v squared over c squared. Let's rearrange that a little bit. We want to solve for v. So let's multiply on both sides by 1 minus v squared over c squared. And then let's divide on both sides by gamma squared, which gives us 1 minus v squared over c squared equals 1 divided by gamma squared. Okay, so let's add v squared over c squared to both sides and then subtract 1 minus gamma squared from both sides. So v squared over c squared equals 1 minus 1 over gamma squared. Let's multiply through by c squared. We have v squared equals c squared, 1 minus 1 over gamma squared. And of course, we can just now square root both sides to figure out what v is. V is equal to c times the square root of 1 minus 1 over gamma squared, like this. Okay, so next, let's plug some numbers in. If gamma is going to be equal to 1.10, what speed does that correspond to? Well, v is equal to c times 1 minus 1 over 1.10 squared. That's the gamma value we're plugging in. If you work this out, it ends up being 0.417 c. That's telling us that we're going at 41.7% of the speed of light, which is really fast. But again, the gamma factor has barely gone above 1. To put this in meters per second, we have 0.417 times c, which is 3.00 times 10 to the 8 meters per second, which gives us 1.25 times 10 to the 8 meters per second. On the other hand, if gamma is equal to 3, okay, now v is equal to c times 1 minus 1 over 3 squared. So that turns out to be 0.943 c. So now you're moving at 94.3% of the speed of light. So if you want to put this in meters per second, it's 0.943 times 3.00 times 10 to the 8 meters per second, because again, c is equal to 3.00 times 10 to the 8 meters per second. That's light speed. Okay, so crunch those numbers, you'll get 2.83 10 to the 8 meters per second. But as I said before, you're going to find there's no value of gamma that can give you a speed that's greater than the speed of light. That just doesn't happen. So let's do another example that deals with time dilation. So a muon is an unstable particle that decays a short time after it is created. So this diagram here shows us the decay of a muon. This mu represents the muon particle, and it decays into these smaller particles, as you see here. We don't need to understand the details of this. This is called a Feynman diagram that shows us how the muon decays into other particles. But the point is, the muon only lasts for so long before it decays. The average lifetime of a muon at rest is 2.20 microseconds. That's the time it takes for the muon to decay, as measured in the muon's own frame of reference. Now, let's suppose that a muon is moving at a speed v equals 0.600 c relative to the laboratory, so 60% of the speed of light. What is the lifetime of the muon as measured in the laboratory frame? And then as a follow-up, how far does it travel before decaying in this frame? So let's work this out. Okay, so let's be super careful about how we set this problem up. So first of all, there are two events that we're considering here. Event A is the muon is created. And then event B, the muon decays. So the lifetime of the muon, how long does it last, is delta t, which is equal to TB minus TA. It's the time interval between the muon being created and the muon decaying that defines the lifetime, okay? And that's what we want to know. So in the muon's frame, so if we imagine a frame of reference that's moving with the muon, these two events happen at the same location. So in the muon's frame, we have what's called the proper time. So
So that's delta t naught, and we're given the value of this. It's 2.20 microseconds. So that's the time that passes from the muon being created to the muon decaying. That's the lifetime of the muon in the muon's own frame of reference. Okay? Now, in the lab frame, the lifetime is different. And we can see how the lifetime changes by using the formula for time dilation. Delta t is equal to gamma times delta t naught. That is, delta t is equal to delta t naught over the square root of 1 minus v squared over c squared. Now here, v is equal to 0.600 c. So to calculate the lifetime in the lab frame, we have delta t, again, is 2.20 microseconds divided by the square root of 1 minus, well, this would just be 0.600 squared, okay? So if you work this out, it's 2.75 microseconds, or 2.75 10 to the minus 6 seconds, because micro is 10 to the minus 6. Okay. Now let's answer the other question. We got the lifetime of the muon in the laboratory frame, and it's longer. And so, how far did it travel? Well, remember, speed is distance over time. Symbolically, we can say v is equal to delta x over delta t, which means delta x, the distance traveled, is v times delta t. So in this case, delta x would be the speed of the muon, which is 0.6 c, or 0.6 times 3 times 10 to the 8 meters per second. That's the speed, 0.6 c. And then we'll take that and multiply by the time, 2.75, 10 to the minus 6 seconds. That's how long it lasts in the laboratory frame. So you multiply these numbers together, and you get 495 meters. So that's how far it's traveled relative to the laboratory frame. Now, let's take it a step further. All of these calculations are relativistic. We're using the theory of relativity to make these calculations. But what if we used Newtonian physics? Well, in Newtonian physics, there's no time dilation. Which means delta t and delta t naught, the lifetime observed in the muon's frame or the laboratory frame, doesn't matter, would be the same. So then delta x would be the distance we would see the muon travel before decaying is still v times delta t, but again, this time we're not talking about a different value of delta t, we're talking about 2.20 microseconds. So v is 0.6 c, 0.6 times 3 times 10 to the 8 meters per second, times the time, which is 2.20, 10 to the minus 6 seconds. And this would give us only 396 meters. So if we ignore time dilation, then the prediction is that the muon should travel about 396 meters in the laboratory before it decays. On the other hand, if we do account for time dilation, so with time dilation, then we expect the muon to move a little bit further, 495 meters before decaying. And that's because it lasts longer, it has a longer lifetime, so it therefore can travel further. So of course, with time dilation is the correct answer. When we ignore time dilation, that's incorrect. So this is how it works in reality. The muon travels a greater distance than you might expect it to because of time dilation, because it lives longer than you'd expect it to. It can travel further. So even though time dilation may seem like a very strange idea, the evidence for it is very solid. This has been experimentally verified many, many times. So time dilation occurs whenever you have two frames of reference that are moving relative to each other. That relative motion causes the two different frames of reference to differ in how they measure the passage of time. Again, this has been verified many times. This is not even controversial in physics anymore, even though it's a very weird idea. So let me give you a few examples of time dilation being measured experimentally. So the first is clocks on Earth will actually tick faster than clocks on satellites that are orbiting the Earth. Again, there's relative motion between a clock here on the Earth and a clock in a satellite that's orbiting the Earth. And we can measure that. It's been shown it works exactly as Einstein predicted. And in fact, we need to account for that difference in the time that passes here on Earth compared to the time that passes on a satellite that's moving around the Earth when we design GPS, because the timing has to be very accurate on GPS systems. You need to account for time dilation to make everything work properly. And another example is in the decay of muons. So muons are actually created all the time in Earth's upper atmosphere. The reason for that is there are high energy particles called cosmic rays, which are flying all around space. Sometimes they'll collide with Earth's upper atmosphere. And when that happens, it creates a shower of very high energy particles that move down towards the Earth. And some of those may be muons. The thing is, we can detect those muons that are created in Earth's upper atmosphere on the ground, even though, according to non-relativistic physics, we shouldn't be able to detect them because they should decay before they ever even reach the ground. So the fact that we can detect them on the ground is evidence for time dilation. The fact that they're moving so fast towards the ground makes their lifetimes longer, means they can actually reach the ground before they decay away. Okay? This is a good piece of evidence for time dilation. And so that takes us to the correspondence principle. Now, time dilation is just one example of what we call a relativistic effect, meaning this is something that we can only really account for if we use the theory of relativity. Time dilation can't be explained, for example, by Newton's laws or anything else. It's a relativistic effect. These relativistic effects are only significant when speeds are close to the speed of light. Otherwise, they're not that significant, and you can basically ignore them. So the correspondence principle says that in the non-relativistic regime, that means when the speeds we're considering are a lot less than the speed of light, Einstein's theory should give the same results as traditional Newtonian physics. Because of course, we already know Newtonian physics works pretty well when the speeds are a lot less than the speed of light. So Einstein's theory should correspond with that. It should give the same results as Newtonian physics in that limit where v is a lot less than c. So in the non-relativistic regime, the gamma factor is going to be approximately equal to 1, as we saw earlier. So if we take the example of time dilation, where delta t is equal to gamma times delta t naught, well, if gamma is about equal to 1, that means delta t is about equal to delta t naught, meaning there is really no disagreement in the time that elapses between the two frames. They measure about the same thing, approximately, which means time dilation is negligible. That's exactly what we'd expect, again, in the non-relativistic regime. So the correspondence principle, in fact, works. So here's a question for you guys to think about. The International Space Station orbits the Earth at a speed of 7.66 kilometers per second relative to the surface of the Earth. What is the gamma factor in this scenario? So try to work this out, see what you get, and then we'll go through it together. So let's take a look again at the speeds involved. The International Space Station, ISS, is moving at a speed of v is equal to 7.66 times 10 to the 3 meters per second. That's the same as 7.66 kilometers per second. On the other hand, light moves at a speed c, which is equal to 3.00 times 10 to the 8 meters per second. So it's very clear that the ISS moves much less than the speed of light. V is a lot less than c in this case. So we'd expect this to be the non-relativistic regime. So let's calculate the gamma factor in this case. Remember, gamma is 1 over the square root of 1 minus v squared over c squared, which is 1 over the square root 1 minus, we have 7.66 10 to the 3 meters per second squared over 3.00 10 to the 8 meters per second, and then square that. Meters per second units will cancel. We just get a pure number. So gamma doesn't have units, it's just a number. And it's equal to 1.000000003. So what are we seeing here? 9 zeros, then a 3. Gamma is really freaking close to 1, right? Almost 1. Barely different from 1. So yes, this is the non-relativistic regime. Now let's think about this. The ISS, from a human perspective, is one of the fastest moving objects we can think of, right? I mean, 7.66 kilometers per second is very fast for human scales. Almost nothing else goes that fast on human scales. But still, it's so much less than the speed of light that we're in the non-relativistic regime. And that means the relativistic effects, whatever they might be, are very, very small. That's why it's very hard to notice these effects. We never notice time dilation in our everyday lives because things are never moving even close to the speed of light in our everyday lives, okay? So according to the correspondence principle, Newtonian physics works perfectly well to describe motion of everyday objects that don't move close to the speed of light. So, as you're probably starting to notice already, and you'll continue to see this as we go on in this lecture, the theory of relativity is very counterintuitive. A lot of the things we're going to learn about go against your intuition for how the world works. And the reason for that is in our everyday lives, we never encounter objects that are moving even close to the speed of light relative to us. And that means relativistic effects like time dilation are always very, very small. They're things we don't even notice. In fact, you'd have to prepare a very delicate experiment to even measure time dilation for earthly objects, okay? So we don't really develop an intuition for relativity just by going out there and living our lives, okay? So MIT developed a game called A Slower Speed of Light, which basically asks the question, what would things look like if you could walk around in a world where you're actually moving pretty close to the speed of light? So in other words, if the speed of light were much, much less so that it were around your walking speed, what would that look like when you walk around in that world? So this is an open source game. You can download it for free and try it out. And I think it gives you a really nice idea of what some of these relativistic effects actually look like. So I encourage you to download this game, mess around with it, so you can get a little bit of an intuition for relativistic effects. So that's all we're going to do for this video here today. We're going to continue with this lecture in the next one. So I'll see you then. Until then, take care as always. Be safe out there. Be healthy. See you later.